take that for a little bit of time. All right, Joe, we're going.
Good.
I wanted to get you in focus once you stand.
All right, everybody. This is Joe Grand, and the title is Using Superpowers for Hardware Reverse Engineering. Woo! Take it away.
What an awesome introduction. My name is Joe Grand, and this talk is using superpowers for hardware reverse engineering. Okay. Thank you guys for dealing with the technical difficulties. So, I do computer stuff. I do electronics. I do hardware hacking. This particular talk is kind of an interesting conglomeration of some experiments that I did as part of some hardware reverse engineering, circuit board reverse engineering work for my cyber fast track project. I had to hop on the cyber fast track bandwagon and get paid to do stuff that I was going to do anyway, but have your tax dollars pay for it. Thank you. Except Zaz, because he doesn't pay taxes in the US, I think. Oh wait, I shouldn't say that on camera, should I? Okay, so yeah, this talk is basically about using some technologies that are not traditionally used in the hacker world to give us information about hardware products or circuit boards. So superpowers, things like lasers. I think there must be some superhero that uses lasers. I didn't actually look in the Wikipedia list, but yeah, lasers, sound waves, X-ray, things that are like usually used in the failure analysis world, the manufacturing world during product development to check on the quality of components or the quality of soldering on a board, but not really at a level of like hackers going in and using these things to say, oh, I wonder what's underneath that epoxy, or I wonder if there's some hidden mechanism that I want to that I might see with X-ray or something with some non-destructive method. So yeah, this talk is sort of like the full work, the cyber fast track work. I'm giving a presentation on Sunday at DEF CON, and then the formal paper is going to be released at Woot, Usenix Woot, the week later. And that's basically all of the techniques that worked to deconstruct circuit boards and get down to different layers of the circuit boards, which is part of the reverse engineering process. But the stuff here is the stuff that either didn't work for that, or that had other uses other than for the PCB, specific PCB work. And I thought it was cool to sort of put this talk together as kind of the B-sides of, the research I was doing. And it turns out there's lots of cool technologies that are available to us if we know where to go and if we have the money to go and, rent some equipment. But as you'll see, it's sometimes not as easy as just walking into a place and throwing money at them and and having them use the equipment for you. So hardware reverse engineering, just a little background. Why would we even want to do it? We all know that software reverse engineering is cool. Network stuff is awesome. There's a few of us in here that I know like hardware, but it's an area that is very wide open. If you're looking to get into something and looking to find vulnerabilities and you're frustrated that somebody else is finding all the buffer overflows and things before you should get into hardware because there's tons of problems. There's lots of other work on my website, lots of presentations about the hardware hacking process and how to go through and analyze devices and reverse engineering and stuff like that. But basically, the main reasons, there's lots of them, but the main reasons either maybe you want to figure out how a system works or how a product works. Maybe you want to use some of these techniques to find a particular connector on the board. So maybe a JTAG interface or a console serial TTL level serial output that typically is used for like a root console or debug output or something. Maybe forensic analysis. Maybe taking a look at a board, either to make sure that it hasn't been tampered with, or look at a board, analyze it, figure out how it works, to find a way that you can inject your own extra functionality, malicious functionality, sort of like our friends at the NSA have been doing for a long time, and probably other governments as well. So, taking an off-the-shelf piece of hardware, analyzing it, figuring out, oh, how can I add extra stuff to that to make it do something surreptitious that the user doesn't know? So all sorts of reasons. How do you do it? You access the product, figure out how to open it, get access to the circuitry, look at the circuitry, see how things are connected, look for interesting things on the board. Sometimes you do need to get to the actual board level and take each layer down and get images of each individual board layer, and then you can sort of superimpose those on each other and figure out how connections are done there if you can't, visually recreate what's going on. So there's all sorts of different reasons, all sorts of different techniques, and this presentation just sort of covers some of the fun, non-traditional stuff. So I have a quick introduction to PC board construction. Circuit boards are basically layers of conductive material, usually copper, laminated, glued to non-conductive material, usually a fiberglass epoxy weave. So it's sort of this sandwich. I like to say it's a circuit board sandwich, and could also be like this Indonesian layer cake, spekok, I think it is. And I got this at a restaurant once, and I said, that is so cool. Looks just like a circuit board. And tastes way better than a circuit board. But yeah, I took like 1 million pictures to get just the right one for this presentation. But different layers of material. Here's a cross section of a board, 16 layers in that board. Boards can basically go from a single layer board, copper on just one layer, more standard, maybe a 2 or 4 layer board where you have copper, alternating a few different layers through the board. You can go up to 16 layer. I think that the largest layer count right now that's practical is like 80 or something like that. That's a lot of layers. And I think they call that like ultra multi-layer or something like that, like mega multi-layer, some crazy term, because like people don't normally do that. You'll see that maybe in like super high-end, maybe like server equipment or some weird military device or something, but usually not 80 layers, like 16. Sometimes in test equipment, like low volume, one-off test equipment type of things for testing chips or something might have tons of layers, but normally you don't sort of get to that level. But yeah, completely crazy. And boards, yeah, by the way, they hold the components, right? We know that when you look at a circuit board, they're holding the components on there, but they're also forming the physical connections between them. So sometimes when I try to explain circuit boards to people that aren't technical, I show them a bare board, and they go, oh, okay, so that's the product. It's like, well, actually, no, you got to put the parts on it, and then, it has to do something. So it serves a dual purpose. It's the carrier, and it provides the connections between everything. Here's another view. There's a bunch of other layers as well. So instead of just, along with copper and the substrate, you have some other stuff. And I'll sort of go down from the top, just so you sort of get an idea when we do some of these, when I go through some of these experiments that I did, it will make sense, like why we're actually doing it. So top layer, we have the silkscreen layer. That usually contains component information, part designators, things that the manufacturer might want on there or make their jobs easier when they're identifying things on the board, things the engineer might want to put on there, pin out maybe a notation of where a particular connector is. So on this board here, you can't really see it, but there's part designators that uniquely identify each part on the board. There's test points. And test points are usually put on interesting signals that an engineer or that a manufacturing facility or a test or programming facility needs to access. So usually if you're looking at a board, you want to look at the test points first, because engineers will only put them on things that they need. So silkscreen, yeah, there's part markings and stuff, but you'll see lots of interesting things on the silkscreen. So that's the first layer. Second layer is the solder mask, green coating on here, but the solder mask now comes in all sorts of different colors as well. And that basically is a protective coating to cover any areas of the board that don't want to be exposed to the outside world or to the environment. So it's really protects the board from dust and moisture, but then it will break out and expose the copper connections that need to be there so you can solder on the components. So things like this along, these sort of green looking traces are the actual copper traces, but they're covered over with solder mask because they're not intended to be handled or measured or manipulated or anything by the user. So if you wanted to get access to those, you'd have to scrape off the solder mask, which isn't really a big deal. But you'll see how we can do it in a much cooler fashion. So then after that, you have your layers of copper and substrate. There's different thicknesses of copper depending on a number of factors, but mostly the current carrying capacity that needs to happen on those traces. Different surface finishes. So sometimes you look at a board and it has gold pads. Sometimes they're silver pads. Sometimes they're a little lumpy if solder has been put on them. So different surface finishes just to aid in the solderability of components. And then substrate, normally I mentioned, is fiberglass epoxy weave. But other times, depending, it could be like some other crazy composite materials, especially for like highly integrated mobile phones, RF devices that have all sorts of crazy characteristics and requirements. Also, some circuit boards now, it's possible to embed some discrete components into them. So into the substrate, you could have resistors and capacitors and other crazy stuff in there. Usually the substrate material plays a part in creating the capacitance or creating the values of those things. But in general, we're normally dealing with epoxy and fiberglass weave. All right, so we're going to look at some lasers first. Shooting things with lasers is awesome. So I figured, why not try it on circuit boards and see what happens? This one in particular, I had gone to a facility in Milpitas that down in Silicon Valley that specializes in using lasers to cut flexible circuits and to make markings on tiny little markings on parts and things like that for the tech community. This particular machine is an LPKF laser machine. LPKF also makes PC board prototyping equipment, which is pretty cool. But this isn't really that much different than a lot of the lasers that you'll see in hacker spaces, that you're using for engraving or cutting acrylics or, whatever. It's just a lot bigger and comes with a guy to control the machine. So this place, I was curious about, like, what can we do? I wanted to see if I could remove solder mask, and I wanted to see if I could remove layers of material. So this was solder mask removal. This particular machine, yeah, there's a picture of it. It's not really that exciting when it's actually working, but it's cool to see the results. And this was pretty straightforward. So we stuck a board in there, did a single pass at medium power. I don't exactly know what medium power is because the operator wasn't exactly sure. It was just there was a low. And the copper layer remains pretty much fully intact. So it was sort of cool. But it's also sort of excessive because using a laser to do what you could do with sandpaper or with a knife or something is sort of ridiculous. But I did want to just see what could be done. Here's an iPhone 4. I'll show the iPhone 4 a few times through this presentation. Small board, 10 layer, ridiculously thin, very complex board, and a much thinner layer of solder mask. Just everything is much smaller. All the feature sizes are smaller, so it was like a good challenge to do. So we threw that in there as well, and that removed the solder mask. This particular connector had solder mask covered over it, which tells me when I'm looking at a board and there's a connector but there's solder mask over it, tells me, okay, that was probably used for development. Maybe the engineer had something plugged in there. Maybe it was a JTAG interface. Maybe it was some other development tool. And then they kept the board the same and just covered it over with solder mask during production. So that's something, if you are analyzing boards, you might go, oh, wait, why is there something covered under solder mask? I want to remove that, tap onto it, and see what it is. That's a common thing. What we found out is if you use lasers too much on something, then it tends to not work anymore. Different materials react differently to different types of lasers. And in this case, we were using a UV laser. And the solder mask in the FR4 would ablate, would get burned away faster than the copper. Meaning we would need to have more passes on the copper in order to burn it away compared to the other materials. So we can't just take a laser across the entire layer of the board and then get access, say, to the next layer, because things ablate at different rates. So we tried to do multiple passes, and the top copper stayed in place, and then we started exposing some bottom copper through there, and it got kind of messy. So there are definitely some downsides, but it was fun to use lasers for that. This example, controlled depth skiving, is a very, very cool technique that is usually used for really, really selective, really, really precise types of material removal. So this is like a tiny laser drilled via, which are used a lot for high-end circuit boards. You can get like a 0.4 thousandths of an inch diameter hole for vias, and vias are holes that are used to connect different layers of circuit boards together. So lasers, usually they're mechanically drilled with normal drill bits, just really small drill bits. But now, because of feature sizes and things getting so small, you have to actually use lasers to burn those holes. So this is one of like a tiny little laser drilled via connected to a tiny little pad. Here's another one of cutting really small connections cutting the flex away, really small connections on a circuit board. A lot of times laser skiving is used as part of a manufacturing process to get a piece of material or get a piece of a product to meet, whatever design specifications it has. This thing on the right, I don't exactly remember what it is, but it's really small. And it's like a comb pattern or something. It's some, I don't know, some plastic type of material. But you can do really, really cool stuff. I was thinking as I was putting this presentation together, which I didn't test, but would have been cool, is that you could probably use this type of technique of controlled depth skiving, of basically etching away or removing material to a certain depth to remove epoxy encapsulation around parts. And I'll show you some examples of epoxy encapsulation for some of the other stuff that we did. But it's basically epoxy put over components or potted around a lot of components to prevent somebody from getting access to them. So if you had a cool laser, usually you could use like a milling machine to mill away the epoxy and use chemicals. But if you had a laser, it would be just better because it's a laser. So for these experiments, I went to a place in Portland called Micron Laser Technology. And I should mention, okay, so normally when you go to a facility or you go to a place that offers services, you say, I'm Joe Grand, I'm working on a project for the government. I'd love to, be able to use your laser to test some things. Rent it by the hour. So most facilities, you can rent services by the hour. So the place in Milpitas to do laser work was by the hour. The X-ray services that I'll show you later, those are all by the hour. One of them was the contract manufacturer that I tend to use for a lot of my products. So I already had a relationship with them. So he was like, well, that's a little weird, but he didn't really care. But normally you go in, you pay by the hour and you do your job because that's America. So for this particular case, I emailed these guys because they had very, very cool, pictures on their website. So like the ones I grabbed for the other slide. And it looked like they really knew what they were doing. Super high-tech stuff. And they deal with a lot of military and government work up there of just very complicated reworking of boards. Sometimes a customer will come in to them and I guess, they'll have like a 36-layer board that's part of some, I don't know, weapons thing. I don't really know. I'm just making that up. But the board is already fabricated. And it's 34 layers, and to refab that board, to make a new board if there was a mistake, could be like tens of thousands of dollars. And if an engineer finds a problem, say they find a problem on layer 6, they need to get to layer 6 or maybe cut a trace or do something. The way to do it is with laser controlled depth skiving, and you can cut down on certain layers and cut things and do like microscopic surgery. So that's a lot of what they deal with, is very secret, very complex types of work. So I emailed them and said, hey, I'm doing some work for the government. My name's Joe Grand. And, I'd like to come up there and see if we can remove layers of a circuit board. So the guy responded. I talked to him on the phone, first, and then we started going back and forth again in email. And, things went quiet for a while. I feel like I need to mention this one. Things went quiet for a while. And I'm like, that's weird. And then I got an email from him. He's like, so I searched your name and you do very interesting things. Referring to the hacker world of things, I guess. I don't know what else. Maybe he found something else. I don't know. I'm assuming he's talking about the stuff I've done in the hacker community. And I'm like, yeah, I do various things. I hack on hardware. This is a project for the government. But he didn't actually believe me. So he's like, actually, no, he started off the email with hi, Kingpin. So, he had done his research. Anyway, so he basically wanted me to prove that this was a government contract before he let me in the facility. And it was this very, a very weird thing. Like usually vendors don't do that to customers. So I was a little caught off guard by that and ended up having to get basically a redacted version of my contract from the company running the DARPA project that I could send to this guy to prove that I was doing the work. So we didn't start off on very good footing because it was like, I'm supposed to be a customer, but I'm being attacked before I even go in there to use the stuff. So if he ends up watching this video, sorry. I didn't feel very good when that happened. Hurt my feelings. So I got over it. I went up there and we did some work. They didn't let me actually see any of the equipment in action. and they gave me these stock images of their machines, though he did let me walk around with him after I, brought my passport and proved I was an American citizen and all of that stuff. It was just a really fucked up experience. I don't know. That's never happened to me before in that capacity. So we went there, and I sat in a room, brought a bunch of circuit boards with me. I basically had 2 of them that I was working with. Oh, I should mention too. So they've heavily modified these machines. It's a standard type of GSI Lumonics drilling machine that's for laser drilling vias, but then they've totally hacked it and modified it, which is funny because they're hacking and modifying things, yet they're treating a hacker as like a total criminal. So I don't know. We're not that bad. We're not bad people. Okay, so I brought 2 different boards to them. What I call the PCBDT board, which is just my PC board deconstruction technique test board, which is a 6-layer board that I've constructed with different test features. I'll show you other pictures of it later. And then I brought the iPhone board. I figured we'd start with something simple, the 6-layer board with very large interlayer spacing. And then the iPhone board as sort of the latest and greatest kind of thing. So I sat in a room and would basically talk to the engineer, and then he'd go out and do a bunch of stuff, and half an hour later they'd come back and show me the result. And that went on, for 8 hours. So the first thing we want to do is like, okay, can we access and expose inner layers of boards? And I thought that we could just go and like shine a laser across the whole thing and get access to the different layers, not knowing about the whole, problem with the energy reacting differently. So the first thing that we did, these 2 experiments were like, can we get access to an inner layer if the board is treated as a black box where we don't know anything about it, there's no engineering data, right? So we get a board and we want to figure out what's on inner layers. That was really hard because of the different types of, because of the laser energy, and we don't know what we're shining through, and we don't know how strong the power has to be. We don't know the inner layer thicknesses and stuff. But we basically removed the top copper with an ultraviolet laser, and then using CO2, different passes of CO2 lasers at usually low energy, to just very carefully start ablating any of the non-copper material, because CO2 won't ablate copper, it'll just ablate the substrate. So our first experiment here, we got a top layer, and then we removed the different layers of substrate, or the thick layer of substrate, and got down to the second layer, where you can actually see there's a via, a drill with a via that's connecting to an inner layer, and then this trace that's on an inner layer going somewhere. So it's sort of cool. It is kind of possible, but this was 0.06 inches by a 1/4 inch long or something like that. A very small space, and that took a really long time. So it's like, you could do it, but large space would just take way too long. Something like this, another really small space, that was on that 10-layer iPhone board. You can see some super tiny traces. These are probably like 2/1000 thick or something like that. Really small. But the same sort of problem is that we can't, really get discrete layer images. So it was, sort of okay. But what was really cool is what you can do if you actually provide the data to the operator. And this is what this company specializes in doing. If they're doing rework, the engineer already has the documentation and says, I need to cut a trace on this layer, I need to access something. So in this experiment, I had a 6-layer board, or that PCBDT board, but part of it I had the 6 layers of Moon Patrol, as you saw on the title screen, each layer of copper creating the layer of an image. So each color that you see on this picture is a different layer of copper, all stacked. So the picture on the front of the slides was the X-ray looking at all of them. But this is like the original design file that I had. So I had 6 different layers. So I said, okay, what if we can remove all of the substrate and leave the copper of those different layers? Would we get like a cool Moon Patrol image or something? So we could do that, but we could only do that if we provided the data to the operator. If I had just said to the guy, I want to expose only the copper, it would take him a really long time. And I think I was paying like $350 an hour or something. And at this point, it was my own money because I had already spent the budget from the DARPA work. So I was just really curious about what could be done. So here's sort of the result. We started with the top layer, which had solder mask on top. So we got rid of the solder mask, exposed the first layer, got rid of the rest of the solder mask, and exposed the substrate. In this board, for some reason, I used I used eTechnet to manufacture these boards, which is the same company I've used for the DEF CON badges and a bunch of other kind of low volume production stuff that I do. But for some reason, they picked this really thick fiberglass epoxy weave that was really, really hard to get through. So you can sort of see the texture as we start ablating down the different layers. Like you can actually see the physical weave, which was pretty wild. So we got rid of the solder mask on here. You can start to see the little vehicle popping through. Once you remove the next layer, you get the copper from the, let's see, that we want to, from the third layer in. And then we started running out of time. So we started doing faster runs of higher energy, which was starting to create some oxidation and some burn markings on things. But we ended up getting, different layers all the way down. And the final one, I was just like, just run it as fast as you can. I got to go. I'm out of money. So the final picture, you can see it started delayering a little bit, delaminating the copper from the substrate because of the heat. But you can actually, with very, very good accuracy, get around and access every individual bit of copper. But that's all dependent on having the data sheet or having the documentation for it. So it's sort of a fun experiment. But if you think of situations where you might need to, access a particular trace on something, or say, you have a ball grid array part that has all of the connections are balls of solder underneath the part, and you've used X-ray, which I'll show you, to determine where a trace comes out that you might need to access. Maybe you use laser like that to drill down to give you an access point of where you can then tap onto the line. Like that's normally what you would do for hardware reverse engineering. So that's lasers. Sound waves, acoustic microscopy. This is a technique that I hadn't heard about at all. But it's a very common failure analysis technique used to mostly make sure that components are built properly, the quality of the components, and if there's a failure, it's used a lot to see, why is the component failing? So some examples down here. This third picture is a silicon die that has a big crack in it, and acoustic microscopy works really well to be able to see cracks in things and to see voids or like air gaps in things. So if components have somehow gotten some moisture in them, and then the moisture evaporates and creates like an air gap. So there's all sorts of lamination issues that you can find. And basically, what the technique is shining ultrasound or sending ultrasound through a liquid coupling medium, so water usually, through the part, and then capturing the sound as it comes through the part, which is called the through scan. But what you can do, and that's sort of the same as X-ray, which we'll talk about, but you can do also is capture the reflections. So you send sound down and then you capture the sound back up. And that's how you can see other types of views. So you have either through scan or reflection, and we sort of experimented with both. So I used a place in Santa Clara called Sonolab. And this was sort of fun. They manufacture the equipment, this acoustic microscopy equipment, but then they also rent out time. So I showed up and hung out with this guy for a little while. It's weird. Everybody I work with has a black square on their head, but they don't talk much. So yeah, I brought in a bunch of stuff, and he pretty much right when I told him what I wanted to do, he was like, "That's probably not going to work to be able to view layer images, but you can use it for other things." So we sort of had a discussion about that. He was sort of fun. And I'll show you the results of that. But he basically has the machine, and then that has the board. There's our target in there, the board. And then he is basically controlling different views and adjusting the frequency of the ultrasound to see different image types, to see if we can try to like get something good out of our images. So for this one, I used an EMIC2 text-to-speech module, which is the speech synthesis module I designed for Parallax. It's a 4-layer board. And I knew, I had the design files, so I could try to correlate exactly what was going on. So we did the ultrasound through it as a through scan and as a reflected scan, and just couldn't really get anything useful that we couldn't already see with the naked eye. And the main reason there is because with too many, so acoustic microscopy works better if the fewer number of interfaces you have, right? So the sound waves come in, the more layers it has of different stuff to go through, sound waves start bouncing off in different places, and by the time you get all the way through, it's just like a complete mess. So he likened it to sticking your face in a pillow and yelling, where it's just like, maybe someone will hear you, but not really. It's much better to just yell. So that's sort of what happens. We're just putting sound waves into this material, and it just goes all over the place. So we got multiple interfaces, layers of boards, nothing really useful there. So I was like, well, crap, none of this stuff's really working. But I brought a bunch of other stuff along with me as well, not just circuit boards. And this is where things actually get interesting. I had this thumb drive, probably from a conference or something, probably containing malware, which is why I opened it. And it had, on one side, it had a flash memory controller chip, like a standard type of chip that you would see inside of thumb drives. That is, it has, USB control and then can interface with the flash chip. So that's this image down here, the bottom one. And on the other side, there was some block of epoxy covering something. I didn't know what. So I had first actually brought this to the X-ray facility when I was doing all the X-ray stuff. And we put it in the X-ray, and the operator saw this image. And I was like, well, I want to try to see what's in the epoxy. And we put it in, and all we could see was the controller chip on the other side that we could visibly see anyway. So she's like, well, I guess there's nothing under the epoxy. And I'm like, but that's weird. Like, why would that be? She's like, I don't know. So she was very, X-ray focused on only trusting the results from the X-ray, which it turns out X-rays don't work very well with, just they won't, the glass and silicon doesn't really absorb much, so you're not going to be able to see much. So we did it again at the acoustic microscopy place, stuck it in there, and it actually turns out that there was a silicon die with no package around it, just a bare silicon die wire bonded down to the board and then covered with epoxy. So this is a top view of the flash memory chip. So if you scraped off the epoxy or used chemicals or something, you would actually see the individual die. Like if you do a search for a die image or something, or chip hacking, or look at any of Chris Tarnowski's talks, you'll see what the die looks like. So there actually was something there. X-ray totally missed it. Acoustic microscopy didn't. And that might be useful not only to know what's under the epoxy, but maybe to know the location of something under the epoxy. And the reason that worked so well is because it was a single interface, so the epoxy covering the die, and then that system just works really well to detect silicon, whereas X-ray doesn't. So that was kind of neat. Another thing you could do, this is a large piece of epoxy over a pin pad device that I brought, and I was hoping to be able to see inside and see the locations of components and see what was inside. But in this case, since this system is really to design voids and gaps, it's like, all right, maybe we could put something in and see if there's any part markings on the inside of the board, which you can't really see them on here, or if there's any weaknesses in the way that the epoxy was poured, and maybe there is a gap that then we can physically take advantage of by, shoving a screwdriver in at that portion to help weaken the epoxy if we're trying to take it off. So that's sound waves. And then X-ray. I like this one the best. So you'll see certain types of X-ray aren't really that good for looking at boards, but they're good for other things. It's all about, all these different technologies, all these different techniques. Some are good, some aren't, just like anything else, right? You just got to have the right tool for the job and know which ones you can use and which ones, aren't going to work. And I spent the money for you, so you don't have to go through the pain. So 2D X-ray, we're all familiar with X-ray, or at least avoiding it at the airport, so we don't have to go through it and getting free massages and free gropes. But, obviously X-ray is used to be able to see through images or see through materials. In the technology world, we use it for PC board assembly to make sure that ball grid array parts are correctly soldered on boards, that there's no solder joints underneath components that we can't see. Also for other types of failure analysis of looking for cracks and other things in circuit boards and stuff. So, it's used a lot, and most contract manufacturers that assemble circuit boards will have an X-ray machine at their facility. And that's why I ended up using the X-ray for this experiment, because they need it to, make sure their assembly processes are right. So this is sort of equivalent to the through scan of acoustic microscopy, where you're sending X-rays through and then capturing the result on the other side. So you get a composite of the entire image. So here's an example, my logo on the test board I had on the top side and on the bottom side. So the image you get shows both. Here's one I use, Sonic Manufacturing in Fremont. This is the machine. And here's inside the chamber. You can put a bunch of different boards and then, adjust the X-ray head and everything. So what you can really do is kind of get a general sense of what's going on a circuit board or inside of a product. So the first thing is just kind of general inspection. This turns out it doesn't work very well to extract individual layers, but it works well enough where if you get a board that you don't know what it is, or you get a product that you don't know what it is, you stick it in an X-ray machine first to get a sense of what's inside before you just try to crack it open. So this one I enjoyed. This was from a Verifone pin pad 1000 SE. I picked up a bunch of different pin pads from different vendors to just experiment with because they tend to have neat anti-tamper mechanisms and neat security features that would be kind of fun to play around with. So this one in particular, when I opened up the unit, there was this circuit board screwed down on top of a bunch of other circuitry. So it was sort of like this active mesh kind of weird circuit board acting as like physical security. And like active security envelope, active mesh stuff is really common on silicon at the chip level to prevent somebody from getting in there and manipulating and measuring, bus lines and address lines and manipulating control lines and stuff. But you don't normally see it that much at a physical level, mostly because it just costs so much money. But for the financial sector, the pin pad, vendors are so paranoid about somebody going and physically modifying a pin pad, which is funny because now there's so many other ways to do it, right? You just take over the point of sale or you inject malware or whatever. So the sort of physical attack has somewhat become obsolete, but there have been examples of people, taking a pin pad, bringing it back, modifying it, putting it back into service, and now it's like logging pins and capturing those for later. So they're protecting against very specific types of attacks, which are done specifically against one unit, not necessarily. This isn't going to really prevent somebody from getting access to that circuitry to continue the reverse engineering process, to pull out firmware, to figure out how it works, to find a vulnerability for something else. But it prevents somebody from going in to the store, quickly opening it up and modifying it. But this thing is like, this weird circuit board. I had no idea what it was. I did end up finding a patent application by Verifone for what they call anti-tamper protected enclosure that says a separate PCB containing one or more unique trace layouts used to create a secret pathway of a specific impedance. And then inside the patent application showed all the details of how the system worked, because patents are supposed to, they exist to share information with other people so they can reuse your work and build on it for, in exchange for license or whatever, even though they're not really used that way. So all the information was there about the system, and I am pretty sure it's talking about this particular board that I found. So I brought it over to the PC board facility when I was doing the X-ray experiments, and I was like, well, what's inside that board? So we put it in. It turns out it's a 4-layer board. It's a little hard to see in here, but there's 4 layers of basically like a maze. A maze has just right angle, weird connections all over the place. So it's like 4 layers of a maze, and then they all come out to 4 sets of connectors on the sides. And underneath these pads, there's 4 pads on each one. So there's lots of different connections going on there. So that was really cool. That's sort of that's actually one step. I took this a step further when I was sort of experimenting with offshore facilities who claim that they can reverse engineer boards, like places in China and stuff. And I sent this to them as well to see what they could come back with. So I actually have exact Gerber plots, the exact PC board layout of how this system works. So maybe use that as the first step, and then you figure out how it works, then you figure out how to defeat it, and then you can take advantage of it. So that's really what, 2D X-ray is really good for, that kind of general inspection. For simple boards, if you do want to trace out where something goes, like a BGA part, or maybe there's a connector somewhere, you want to find out where it goes, and there's multiple layers, it's a really cool way to do it. But because we're looking at a composite image, it's hard to see which layer something is on, but sometimes it doesn't even matter, right? So in this case, say we have here's our ball grid array part. Say we wanted to access this pin, which we would know which pin we want to access by potentially looking at the data sheet for the part and seeing, oh, that's a serial output, or that's a JTAG pin, or that's a pin. If we pull that high, we can load new firmware. So we would use the X-ray, take a look at the trace, see where it breaks out somewhere else on the board, and then we tap in at that location. You can also, which is cool, like usually you don't think about this, like when you go to the doctor and get an x-ray of your arm or whatever, you just see like a single image. But what you can do when you're actually at the x-ray machine, the operator can change the angle of the x-ray, change the field of view, so you can sort of zoom in, zoom out, manipulate where we're looking on the board. So you could actually, with simple boards, you could try to figure out exactly where things are going. It will just be time consuming, but it's actually pretty cool. Because you sort of just assume it's like a static thing, but it's not. Here's some other examples. This is that 4-layer EMIC2 board. A little hard to see again, but there's layer numbers that I put, and I'll show you a better picture on the next slide. Sometimes circuit boards will put layer numbers on the different layers of the board. So they'll put copper numbers for each layer of the board. That helps with the engineer knowing what they're working on. It helps the board fabricators know when they're putting the different layers of the board together, which order they go in. So that's useful. We can sort of see those. You can actually see the different vias connecting different traces together. But again, you don't really know what layer things are. Here's an assembled iPhone board. Now that we know X-ray doesn't work too well to actually see the silicon dies, we can see through those and see, a lot of the locations of things. But it's still not that great at such a complex level. Here's some other cool things. This is just looking at a hole, like zooming in on a hole on that iPhone board. And that iPhone board is 10 layers. So there's actually 10 different shades of gray. Too bad there's not 50, but we're getting there. 10 is good. 10's good for now. So you can actually, if you encounter a board and you don't know how many layers it is, you could look at a hole, or you could look at the edge of the board and see individual copper planes. It's sort of like doing a cross-section, but it's a non-destructive way of doing it. So if you only have one board to mess with, or you don't want to chop a board in half to try to see the layers, you can do it with X-ray, which is kind of cool. Here are some layer images, or layer numbers. It's 1 through 6. They're sort of stacked on top of each other, and then we angled the field of view so you can kind of see them. Down here are things called stacking strips, or stacking stripes, or stacking stairs, depending. Which is sort of a trick. It's a PC board design trick. So for each layer of your board, you put a different length strip. So say layer 1 has the shortest, layer 2 is slightly longer, layer 3 is slightly longer. So the board fabricator knows that it should be in a increasing length stack. If you're analyzing it, so this is common. So if a board comes back and it doesn't work, you X-ray it, and if you notice the long stripe is in the middle, then the board fab fucked up. And that will save you a lot of trouble. But then from a hacking point of view, we can use that to figure out how many layers there are, interlayer thickness, and stuff like that. Because you can actually take measurements at this point too and figure out, lengths of things. Examining through epoxy is another great use of X-ray, of 2D X-ray. This is a classic example. I love it. This particular one is, you guys know Pac-Man? Yeah, okay. Like 2 of you. Yeah, Pac-Man. Okay, so this was an upgrade for Pac-Man Plus, or upgrade for Pac-Man that would enable the arcade game operator to now have Pac-Man Plus. And what it was, Bally Midway had this thing. It was like a 1/2-inch thick block of epoxy that you would replace on the motherboard. So you take out the Z80 processor on the board, plug in this block, and then you had 6 ROMs with the program code on there, but the ROMs were scrambled, so you couldn't just copy the ROMs and put them in a normal Pac-Man machine with a regular Z80. This block was doing some sort of scrambling, obfuscation, encoding, something. So it's sort of like an early DRM kind of thing, right? Of preventing people from just ripping off the ROMs and getting Pac-Man Plus for free. And this is actually a good example of really good security, because I don't know if anybody was actually able to figure this out prior to when Clay Cowgill did it, when he, did this work. So it's sort of a, kind of a good example of security actually working for once, which is neat. But now technology is sort of caught up and people have access to more equipment that will let them break it. So it was good for 30 years or 20 years, I guess. So in the year 2000, Clay Cowgill, who is a co-owner of Ground Control Arcade in Portland, an awesome arcade and classic gaming enthusiast, got access to one of these and was like, well, I want to figure out how it works so people can play Pac-Man Plus on emulators. Pac-Man Plus, by the way, has different mazes and different characters and stuff. It's pretty cool. So he went about the process. He said, okay, it's a solid block of epoxy. What am I going to do? Brought it to his friend who worked at a veterinary clinic, put it in a little PET X-ray, and got a tiny little, straight shot, straight through X-ray image. And he knew that there was a Z80 processor in there because he replaced that one with the one that was on the board originally. And then he could identify these other parts that were like some sort of logic or CPLDs or something. And it turns out that they were programmable logic to do manipulation of the address and data bus lines, but he couldn't figure out what they were. But from this view, he could say, okay, now I know exactly where that Z80 is. So his plan was to get through the epoxy just in this location so he could remove this part and then put on like an in-circuit emulator or a simulator to basically now he can be the Z80 processor. And then he could say, read from address 0, and then he gets data back of whatever, that's supposed to be. Because at some point, all this obfuscation and scrambling needs to make sense when it gets to that main processor. It has to, execute, it has to receive the data at the address that it wants. So by doing that, he was able to create a dump from address 0 all the way of the unencrypted or unencoded version of the ROM. So now everyone can play Pac-Man Plus on emulators. Here's another view. This is, this is that same device that I used for the acoustic microscopy. Big epoxy blob covering a bunch of circuitry on the board. And usually when you see epoxy on a board, if it's on one component, you say, oh, okay, the vendor's trying to protect that component. Let's go after that. If it's on a block, you say, okay, there's probably interesting things under there. And it's usually microcontroller, maybe key storage, memory, like all the stuff that we want to go after. So X-ray in this case, the acoustic microscopy didn't really show us much, right? We saw some voids in the epoxy, but nothing really that interesting. With the X-ray, we could look through and actually identify a bunch of different stuff. Here's a clock, a crystal oscillator. Here's a chip right next to it. Here's something else. There's another chip. So there's a few major components in there. And I'm guessing, just by seeing this clock, that this is probably the microcontroller here. Because usually you have a clock that creates kind of the heartbeat for the system. Right next to a microcontroller. So that's probably the microcontroller. Down here, maybe that's RAM or flash or something. Maybe it has internal memory. I don't know. Maybe this is some custom chip. But you can see the little bit of the die inside. That's actually that's not the die. That's the substrate or the paddle that the die is mounted to. So it's not the real silicon. So yeah, get general location of things. But then I think the coolest of all of this stuff is 3D X-ray or CAT scans. And, you see this of like layers of people's brains and stuff. But I didn't know it even existed for failure analysis or for X-ray. And when I'd left Sonic Manufacturing after doing the 2D stuff, one of my contacts over there was like, I know a guy right around the corner that does 3D X-ray. Like, you should check it out because he has like the special software package for the tool, for the X-ray machine. Like, it's pretty awesome. So we made an introduction to this guy who runs a company called Day Test. I'll show you them on the next slide. And I did a little research about it, and I called up the company. And the phone number of the company, I think it was on a weekend or something, the phone number forwarded to the CEO's cell phone, who was in Germany at the time at a conference on like X-ray technology or something. So it was like 3 a.m. Germany time, and he answered the phone, and I felt really bad because as soon as I heard the ring tone change from like a normal US ring to the other one, I was like, oh shit. But then I didn't hang up. So he answered it at 3 a.m. and was like a little groggy, and I was like, okay. So I just started explaining the whole situation. He's like, well, I'm in Germany. I'm coming back in 2 days. Come by. So it was like a total very different response than some other of my experiences. So a few days later, I go over there and we throw a bunch of boards in there, and he also had never done it. He was like, okay, well, we normally do things like inspecting solder balls to see if there's cracks in them underneath parts and stuff. And you can actually take, 3D slices of things and recreate things in 3D. He'd never looked at circuit boards through there. So it was a learning experience for him too. And everybody in the company was sort of interested to see what happened. But basically with 3D X-ray with CAT scan, you're taking a series of 2D images and then post-processing them with lots of math to basically give you cross-sections of every single layer or layers through an object, which is very, very cool. You take like 60 to 720 images, depending on the resolution you want. as like the X-ray head moves around the target, and then I'll recreate it. And you can manipulate it with standard like 3D modeling software and move stuff around. Very, very cool. So here's the place. Another guy. It's weird. Maybe they're all related. I don't know. So this is the machine. Looks similar to a regular X-ray machine. Has the working view and stuff inside the chamber. Here's the software that you can use after the fact once you gather all of the traces or all of the segments. Is you recreate, look at X, Y, Z views and manipulate and can see what's going on. So this one was all about trying to extract individual layers of the board. So I brought in again my 4-layer EMIC2. We took 360 2D images, one every 6 seconds, imported all that data into VG Studio, which is the tool they use for manipulation. And then we could manually move through the Z axis or the Z plane and identify each layer of the board, which blew me away. It was totally cool. We could also measure the thickness between layers if we didn't already know that, because we could just count. We knew the step size of our images. And the results will vary depending on thickness of copper and stuff. But here's sort of a sped up view of the X-ray head moving to take different images. And then down here, the results of the different images. And here's we made a little MPEG video. And they gave, the company gave me all of this stuff. They're like, here's a video of the different layers. So now we're moving through the Z axis, looking at like the top layer. There's a top layer, there's the second layer, and then there's a big substrate, in the middle. Then the third layer comes up, and then that was the third, and then the fourth. So you can sort of automatically go through and see them all. And then here's like the final thing is here are the images we've extracted. It's a small field of view, so if you wanted to do a whole board, you'd need to do, multiple segments of the board and recreate it. But in this case, we did a small area. It was like a 1x2 or something like that. And then these are the images we pulled out. And then compare them to the actual image layers from my circuit board design tool. You have 4 different layers and they are exact. Because they should be. So 3D CAT scan, awesome for identifying layers of boards. Okay, so that's the end of the presentation. Those are, the technologies that are kind of just weird technologies, and there's probably more. There's probably other superpowers you could use, but this is the starting point. And yeah, so it was sort of fun. Thanks for being here, and do you guys have any questions? Question?
Were you able to extend this to ASICs?
Was I able to extend it to ASICs? No, but at this level, you'd probably end up seeing the same sort of thing. ASICs being application-specific ICs, which are custom chips. You would end up seeing at that higher level the same sort of, you'd be able to see locations of things or other stuff. As far as like chip-level hacking, I didn't get into that. Because Chris Tarnowski is like the chip level or the chip hacking god. But some of the same equipment, yeah, you could probably, maybe if you decapped the chip and then looked down and used, a focused ion beam machine or something, or scanning electron microscope to get images. But yeah, I didn't do any sort of chip level stuff.
Do you think that you can use the MRI scanning technique to get more information about PCBs?
Yeah, so could we use MRI to get information about PCBs? No, these guys are saying no.
Magnet. It's what happens when you put a bread tie in a microwave.
If you put a tie, whatever. Oh, because it's metal, so everything will spark and stuff? Yeah, so I guess not. Because it's, magnetic and it's ferrous material or something. I don't know. It would be fun to try on someone else's machine, I guess, but... okay, is that it? Oh, he's holding a sign that says stop now. So you can come up and ask more questions. So thanks.